Okay, good afternoon, everybody, and thank you once again for attending the fourth in the series of our CIBSE approved CPD presentations, specifically on the topic of steam. In previous months, we've started off the series of presentations with a very broad and basic introduction to steam fundamentals. We then moved on and we considered the things that we need to do to ensure that we're conveying the steam from the point of generation to the point of use in accordance with commonly held good working practice. And then last month, we looked at the topic of heat exchange, which after all is the principal reason that many of our clients are going to have steam on their facilities in the first instance. And in today's presentation, we're going to move forwards and look at steam trapping, steam traps, which, in my opinion, are the single most important component of a traditional steam and condensate loop. Without a well-designed, sized, installed, selected and maintained steam trap, it's highly unlikely that we're going to have an efficient, safe and reliable steam distribution network. So moving forwards, we've made the introduction to Spirax-Sarco previously. Hopefully you'll remember those useful resources and design tools that we have on our website, and also those calculators and configurators that you can access that are demonstrated by the two little logos and widgets up in the top right-hand corner of the screen. They remind us that those calculators and configurators can be used for two different reasons. First and foremost, we can use those calculators and configurators for design purposes. If we've calculated the amount of heat energy that a particular process requires, by default, we've calculated the mass of steam that's required. And once we know the mass of steam that's required to satisfy the demands of the process, we've sized the heat exchanger, the control valve, the pressure reducing valve. We've also sized the steam trap, the steam pipework and the condensate pipework. And the other reason those calculators and configurators are important is it helps us to calculate our client's cost of steam. Now, in my experience, about 50% of clients, they will be aware of what it actually costs them to produce a ton of steam. 25% will have no idea whatsoever. And what's perhaps more concerning is 25% of our clients will think they know what their cost of steam is, but in reality, they could be way off the mark. So if we've got a steam trap that has been failed in the open position and left failed for any period of time, that steam is going to be vented away to atmosphere to prevent an overpressurization of the condensate infrastructure. So if we know the size of the steam trap and the pressure of the steam distribution network, we know the mass of steam that is being lost. If we marry that up to our client's cost of steam, well, it means that we can determine what that inefficiency is. And that inefficiency isn't just measured by the financial cost of the steam itself. It means that our client's boiler is going to be working harder, consuming more fuel, and of course, those carbon emissions are going to be all the greater. So moving forwards, topic of steam trapping, as I've mentioned, I believe it to be critically important, perhaps more important than the heat exchanger itself. Because if our steam trap is undersized, poorly selected, poorly maintained, poorly installed, it's highly likely to fail. It will have a high cost of ownership, and it's highly likely that if and when that steam trap fails, it will result in those costly and unnecessary emissions. So in today's presentation, we're going to start off with a very, very brief review of the basics, the fundamentals. And I appreciate we've gone through the fundamentals in previous presentations, but it's vitally important to have a recap, especially for those of you that may not have been able to attend the previous presentation. As with the previous presentations, any attendee that would like to receive a PDF of the slide deck and a PDF of the CIBSE attendance certificate, they'll be more than welcome to receive that. If you're able to drop me your details, I'll get that emailed across to you. And similarly, this presentation will be recorded and uploaded to CIBSE's YouTube channel for future reference in due course. So the properties of steam that we've spoken about previously. what sets steam aside as a different source of energy to domestic hot water, low temperature hot water, for example? Well, steam's a gas, and that gas is compressible. So, of course, if we're generating that steam at a high pressure, we've compressed that steam down so it occupies a very small volume. So if we're conveying that steam around a hospital or around a university, it means that we've reduced the infrastructure cost considerably by elevating the pressure of the steam. We also know that there's a pressure-temperature relationship that steam has. We know the pressure of the steam, we know the temperature. We can manipulate the temperature simply by regulating the pressure. We can't do that with hot water. So it tells us why those two-port self-acting pressure-reducing valves are very, very attractive to managing the energy relationship with steam. But it also tells us why those pressure gauges are also critically important. We also know that steam is very, very densely packed with energy. And we know that because steam gives up its heat energy by condensing, and when it condenses, it doesn't cool down. Well, that tells us that there's approximately 50 times more energy in a kilogram of steam than there is in a kilogram of water. So that's useful information for us to remember, because if there's so much energy in a kilogram of steam compared to a kilogram of water, then any boiler doesn't have to produce the same mass of energy that an alternative hot water boiler would. Again, steam's a gas. It moves in accordance with the pressure drop. So if we've got a steam boiler that's operating at 10 bar gauge pressure, if we're using the steam at the heat exchanger at a much lower pressure, thousands of meters away, well, it tells us that the steam's going to move all by itself. In other words, we don't need to pump it, as we would do with an alternative source of energy. And we know that when we depressurize the steam at the heat exchanger, if we depressurize the steam from a higher pressure to a lower pressure, it's going to expand. And as that steam expands, it's going to occupy every corner of that heat transfer surface area evenly and uniformly. And that means that efficient use of the heat transfer surface area, well, it means that we're not at risk of the cold spots or the striations as we commonly see with water-to-water heat exchangers. Because steam gives up its heat energy by condensing, that phase change from gas to liquid, it essentially means that the speed of heat transfer is approximately 3 times greater than with a water-to-water heat exchanger. So if we compare the high energy density, the efficient use of the heat transfer surface area, and the high speed of heat transfer, it explains why steam to water heat exchangers have typically got a footprint that is a quarter the size of your traditional water-to-water heat exchanger. But as far as this presentation is concerned, it's critically important to remember that steam gives up its heat energy by condensing. So it changes state from a gas to liquid. That liquid condensate exists at exactly the same temperature as the steam does. So when steam condenses, it gives up its energy, it changes phase, but the pressure and the temperature of the condensate remain exactly the same. So we've gone through the steam tables previously. And in the previous 3 presentations, we've taken our time to explain the relationship that the steam tables have and their importance. I'm going to skip through these very, very quickly. So moving from the left-hand side of the screen towards the right, the first 2 columns, they really demonstrate that pressure to temperature relationship. If we know the temperature of the steam, we know its pressure, and vice versa. So the next column across, headed water, that tells us how much energy the water needs to contain before it's going to hit boiling point. Of course, we say needs to contain rather than the energy we need to add, because it really depends upon the temperature of the water that we're putting into the boiler in the first place. The higher the pressure, the higher the temperature, and therefore the more energy we need to add before we're going to achieve boiling point. But the steam tables really demonstrate that that energy is not lost. The steam carries that energy to the heat exchanger. The column headed evap evaporation, that tells us how much energy we need to put into that water that's already boiling. We need to put a lot of energy into the water to make it evaporate. But again, that energy is not lost. The steam carries that energy to the heat exchanger. So the final column headed steam, that is the total heat energy content that is present within the steam. So when that steam hits the heat exchanger, we know that it gives up its heat energy. And as it does so, the steam condenses. Now, the energy in the column headed evaporation, that's the useful heat energy that moves across the heat transfer surface area into the process. Therefore, the energy that's left behind when the steam condenses is exactly the same as the energy that we put into the water to bring it up to the boil. In other words, if we're condensing steam at 10 bar gauge pressure, the temperature of the condensate will be 184 degrees, and the energy content of that condensate will be 782 kilojoules per kilogram. Now, that's far, far less than the heat exchanger has been sized to expect. So as far as the condensate is concerned, when it exists at the process, at the heat exchanger, it's unwanted. It's a byproduct. We need to get that condensate away very, very quickly, because if we don't, that condensate is going to back up and flood the heating space. But if we can get that condensate back to the boiler house, then we can keep that high temperature hot water in storage until the boiler has a demand for water to keep in equilibrium with the steam production. In other words, you can appreciate that if we put in that condensate back into the column headed water, we're going to have a significant energy efficiency that we can enjoy. Now, over towards the opposite side of the screen, this is what we refer to as the temperature enthalpy curve. It effectively demonstrates the journey that water takes in the boiler as it changes state from a liquid to give us steam as a gas. And it's critically important, and hopefully you appreciate this from attending previous presentations, but it's critically important that we appreciate the benefits of keeping the steam as dry as we possibly can. Dry saturated steam is critically important. Anything less than dry saturated steam, and it means the steam is likely to exist in what we refer to as the wet steam zone. And if we have wet steam, our client is going to get a number of different problems. And those problems typically sit in two different categories. We've got the mechanical, the maintenance problems. If we've got wet steam, we're more likely to encounter issues with erosion, corrosion, water hammer. We're going to have a lot of maintenance issues and a high cost of ownership of our steam system. If we've got wet steam, we're also going to have inefficiency issues. They're a little bit more difficult to spot. For example, if we're distributing 10,000 kilograms of steam per hour at a high pressure and therefore at a high temperature, thousands of meters around our distribution network, that's essentially one big radiator. We can expect a significant amount of heat loss. If we've got wet steam, we're going to get a lot more heat loss than if we've got dry steam. Therefore, we need to remove a significant amount of condensate from the infrastructure, and we're going to need a greater number of steam traps to install and manage. And if we've got a high heat loss, it could well be that we're generating 10,000 kilograms of steam per hour, but by the time that mass of steam gets to the various plant rooms around site, there may only actually be 9,500 kilograms of steam that's available. 500 kilograms of steam is condensing as a result of that distribution inefficiency. Now, it could well be that that mass is simply not enough to keep the process operational. It means that the steam heat exchangers are now undersized. It means that the boilers may have to work harder to combust more fuel to produce the mass of steam that can satisfy the requirements of the process. And if we've calculated our cost of steam, then we know what that inefficiency is going to look like in financial terms. If we're combusting more fuel to allow for the steam inefficiency of the distribution network, it also means that our carbon emissions are going to increase. The other thing to bear in mind is as that steam's moving around the infrastructure and passing across that trapped condensate, it means the steam is degrading. So it's moving further and further away from the dry saturated steam line and into the wet steam zone. And if we look at the bottom axis, that tells us that as that steam degrades and gets wetter and wetter, it's going to have less energy contained within it. So it tells us we've got a double whammy going on here with wet steam. It tells us that not only are we getting a reduced mass that's available for the process, it tells us that the steam that is available is going to have less energy in it as well. So you can appreciate how that is going to affect not only the process, but it's going to affect our financial cost of producing that steam. So how do we keep the steam dry? Well, in short, one of the best ways that we can keep the steam dry is by removing the condensate with the appropriately sized, selected and installed steam trap. Now, some processes, especially in the healthcare environment, are going to have critical applications. In building services, that's typically going to be the healthcare sector, which can use steam for purposes of humidification and sterilisation. And in those critical applications, it means that we're going to want to ensure that the steam is maintained at the appropriate condition. And as far as HTMO 101 is concerned, that generally uses a standard we refer to as BS EN 285, and that's calling for the steam to exist at a dryness value of 95% or better. So that tells you, once again, how critically important it is that we're removing that condensate using the appropriate steam trap. Now, the slide I'm showing at the moment, we've gone through previously. It really shows the effect of how we're able to generate steam under pressure, thereby reducing its volume. But of course, if the pressure of the steam falls, then we need to ensure that we size the infrastructure to allow for the volume that that mass of steam is going to exist at. So when we think about steam traps, think about a steam trap in the distribution pipework. We're distributing that steam at a pressure of 10 bar gauge. It's got a very small volume. Now we need a pressure drop across that steam trap because the steam pressure needs to be capable of pushing the condensate away from the steam side to the condensate recovery side downstream of the trap. The issue here is condensate is a non-compressible single phase fluid, and therefore the condensate infrastructure is typically significantly smaller than the steam pipework. But if that steam trap were to fail in the open position, any fall in pressure across that steam trap, for example, from 10 bar gauge to atmospheric, that would result in a significant expansion. And the problem we have is if that steam passes across into the condensate infrastructure, that huge expansion is likely to result in a lot of damage to the condensate infrastructure itself. So typically, we're going to have steam vents that are sited periodically on the condensate side with the purpose of allowing that expansion to be vented away to atmosphere. Now, unfortunately, it's a necessary evil. We need to protect the infrastructure from that expansion. But what we can see here is a case where we're losing a significant mass of steam. So our inefficiency is going to increase significantly. And if we've calculated our cost of steam, we know exactly the financial impact that that single failed steam trap is going to have. Now, the other problem we have is we've got a pressure-temperature relationship with the steam. So, for example, if we're producing steam at 10 bar gauge, the temperature of the steam is 184 degrees. If we've got a sterilizer or another heat exchanger, for example, that only requires the steam to exist at 130 degrees, we can achieve that by manipulating the pressure, reducing the pressure down to 2 bar gauge. Tells us why it's critically important that we've got the appropriate number of pressure gauges around the infrastructure, but it also tells us how attractive it is to have those those 2-port self-acting pressure reducing valves to help us to control that pressure temperature relationship. But we need to remember that when steam condenses, it changes state. It gives up its useful heat energy, but it doesn't cool down. The condensate's got exactly the same pressure temperature relationship. So when we get the heat loss in the infrastructure, when we're distributing steam at 10 bar gauge, the condensate's going to be sat there in the pipework as a liquid at 184 degrees. Now it can exist as a liquid at that temperature because of the pressure. So if that steam trap fails in the open position, just as the steam falls in pressure and expands, the condensate too may be falling from pressure at 10 bar gauge to 0 bar atmospheric. So this curve really demonstrates that when that happens, the condensate's got to fall in temperature too, from 184 to 100 degrees. The only way the condensate can do that is by giving up a lot of energy. So that means that a certain mass or a certain percentage of the condensate is got to boil off. Got to change state from a liquid back to steam as a gas. We call that flash steam. So again, that explains the importance of those steam vents that are venting that expansion away to atmosphere. Because as that single phase non-compressible fluid falls from 10 bar gauge to 0 bar gauge, the rate of expansion is going to be to a factor of more than 1,673 times. Without venting that expansion away, we're going to get a lot of damage to the infrastructure. But again, we're going to have a significant amount of energy that's being lost. So it's really important that we keep an eye on those flash steam vents because it gives us a really good understanding of the overall health of the wider steam trap population. But before we move on to look at steam traps in any greater detail, I also want to take a moment to mention why we always consider air venting at the same time as steam trapping, but for completely different reasons. Now, some steam trap types are capable of venting air and others are not because they work on an entirely different principle. The problem we have with air is by far and away the biggest insulator, the biggest barrier to heat exchange that there is. So if we don't get rid of that air, the effect on the heat exchanger, it's like failing to bleed your radiators at home. And it's vitally important that when we're looking at a steam system, we choose an air vent that works on the thermostatic principle and not on the density principle, like air vents that we use on a water-based system. And that's because steam and air have got very, very similar densities, but they've got different temperatures. And the two images that you can see at the far right-hand side of the screen, it really gives us an indication as to where we locate an air vent. We would typically locate an air vent at the occasional high point of the infrastructure and also at the high point of a heat exchanger at the opposite side to the steam inlet. Now, I mentioned that some steam trap types are very good at venting air. But even if we do select a steam trap that's good at venting air, we need to remember that one of the primary purposes of the steam trap is to drain the condensate away. And the condensate is going to fall under gravity to the bottom of a heat exchanger, as you can see here. So such a steam trap would only really be useful to us to drain the air away upon those first few moments when the system is starting up from cold. Once the steam has actually pushed the air past the bottom, then we're likely to have a heat exchanger that becomes airlocked. And that means that we're going to get a slow process time. We're going to get an inefficient release of energy into the process. But it also means that we're going to find a cost of steam that is slowly starting to escalate. So if we fit an air vent at the high point, it means that not only is the steam trap capable of venting air from the low point, but it's also preventing that heat exchanger from our air locking. Like I say, we want to think about air venting at the same time as we do steam trapping, but it means that we also need to allow for the air to be vented away from different parts of the heat exchanger. So one of the questions is, well, why do we need to recover that condensate? Well, as we mentioned right at the start of the presentation, when we looked at the steam tables, there's a significant value to that condensate if we can get it away from the process and if we can get it back to the boiler house. It's hot water. and it's chemically conditioned hot water at that. So as a very, very broad rule of thumb, we know that there's approximately 25% of the energy, of the total heat energy of steam, that is retained in the condensate. And therefore, if we know what our cost of steam is, we know that the value is approximately a quarter that is retained in the condensate itself. The next thing we want to give thought to is, well, where does that condensate exist? Simply put, condensate exists wherever steam gives up its heat energy and condenses. And that can either be in the distribution pipework itself, high temperature, high pressure steam in a steel infrastructure. If we're distributing that thousands of meters, it's inevitable that we're going to get some heat losses. So it is, after all, one big radiator. And of course, the rest of the steam is going to condense and give up its heat energy at the process, at the heat exchanger. And that's a good thing, because that's where we want to use the energy with the steam. So we can apply a typical rule of thumb to determine how much condensate we expect to exist in the infrastructure. Typically, if we know how much steam we're producing, I use the example of 10,000 kilograms per hour, then we would expect approximately 2% of that steam to condense out in the infrastructure. So 10,000 kilograms of steam, 2%, that's 200 kilograms of condensate per hour that we need to remove from the network. So we can use that information to size and select and decide where we want to locate those steam traps. That's what we call the running load. And the running load assumes that the infrastructure is nice and hot 24/7, which of course it rarely is. We're going to find steam boilers switched off periodically. We're going to find different buildings isolated from time to time. And when those boilers are switched on, and when those isolation valves are opened, then a lot of the steam in the infrastructure is going to give up its energy to the pipework before it even gets to the process. And that heat loss, when we're warming the system up from cold, we refer to it as the warming up load. Typically, we would double that running load, that 2%, 200 kilograms, to allow for that massive condensate that is going to be present whilst the infrastructure is warming up. The thing to bear in mind is, if we haven't sized the steam trap capacity, allowing for that increased warming up load, those steam traps are now going to be undersized. The condensate cannot pass, and the condensate is going to back up and slowly start to flood the infrastructure. And that's when we find those issues with erosion, corrosion, water hammer, a high heat loss due to wet steam, and a low energy content of the steam slowly creeping up on us over time. And it's good working practice to apply the same rule of thumb for the process as well. Because if you think of a heat exchanger as a huge lump of metal, it essentially means that if we've got a process that's stopping and starting periodically, it means when that process is starting up, when the steam is energizing the heat exchanger, whilst the heat exchanger is cold, more and more of the steam is going to be lost to the atmosphere and to the heat exchanger itself before it enters the process. So if we haven't sized the heat exchanger to allow for that warming up load, the risk is the condensate is going to back up, it's going to flood the steam space, and we can now no longer get the steam into the heat exchanger. It's flooded with water. So it's going to take longer and longer to get the process up to temperature, and we could be exposing ourselves to a little bit of damage and water hammer in the process. So the steam traps, well, it's a vitally important piece of capital equipment. And it's important to understand that there's no such thing as a universal one-size-fits-all steam trap. Different steam traps operate on different operational principles. They have different capacities. And we need to ensure that we're selecting the correct type of steam trap, because different processes, different applications, they need to stand up to different environmental conditions. One type of steam trap may work perfectly well under one condition, and if the process were to change ever so slightly, it may now mean that that steam trap is no longer suitable and it could be susceptible to failure. So the different types of steam traps, they would typically fall into 3 different categories. We've got the steam traps that work on the thermodynamic principle, the thermostatic principle, and the mechanical principle. So one of the most common, one of the most popular types of steam traps is what we refer to the thermodynamic or the TD trap. Advantages are it's very, very small, it's very robust. The only moving part is the little disc that you can see fluttering up and down in the head of that hexagonal nut that you can see on the screen. It works on the principle that any condensate that is moving across the trap is going to fall in pressure. And as we know from the principles we've gone through earlier, if we get high pressure, high temperature condensate that falls in pressure, we're going to get a little bit of that flash steam that expands. As that steam expands, it's manipulating that little moving disc. It's blowing it up into the top of the trap. And that hexagonal nut is of such a size that it's allowing that flash steam to condense very quickly. As that happens, the volume's collapsing and it's pulling the trap shut, trapping any live plant steam behind it. This is very, very well suited to removing the condensate that exists in the distribution pipework, because as we remember, that's going to be at a high pressure and a high temperature, maybe 10 bar gauge, 184 degrees, but it's going to be a relatively small mass, 2% or 4% if we allow for that warming up load. We'd never use this type of trap behind a process for the simple reason, well, it's not going to be of a large enough capacity, and because it's discharging condensate intermittently, there is a risk that it could cause the condensate to back up and flood the heat exchanger. The other thing to bear in mind is this is a type of trap that can't tell the difference between steam and air. So it's critically important that whenever we're selecting a thermodynamic trap, we think about the air venting upstream. The next type of trap that is very common in building service applications is what we call a thermostatic trap. It works on the temperature difference between the steam and the condensate. So you might have noticed that I've contradicted myself there a little bit, because steam and condensate exists at the same pressure and temperature. So that means we've got to site the trap a couple of meters downstream from the heat exchanger or the point where that condensate's removed. We've got to make sure that that pipework is unlagged so the condensate can lose some of its heat energy and cool down before the trap opens. The cold condensate will pass across the trap. Once the cold condensate's gone, once it's exposed to the higher temperature steam, the little element within the trap will expand and it will lock the steam in. Now, this type of trap is very, very attractive for us to use on heat exchangers that are constantly stopping and starting, because when the heat exchanger is starting up and when there's a high condensate burden, the trap is going to be in the fully open position, which means that we can guarantee that we're getting that air away very, very quickly. Another benefit is a lot of hospitals select this type of trap for energy saving purposes. As we've mentioned, if we get a fall in pressure of high temperature condensate, we're going to get a lot of flash steam that's produced. And that flash steam needs to be vented away. The benefit of this type of trap is if we're allowing that condensate to cool down anywhere between 5 and 20 degrees, we're minimizing the amount of flash steam that will be produced. And therefore, we're increasing the overall efficiency of the system because we can get more of that hot water, more of that condensate back to the boiler house. And then finally, we've got the type of trap that most people are probably more familiar with. It's the mechanical trap. Works on the principle that steam is a gas, condensate is a liquid. They've got different densities. And that difference in density is going to manipulate the buoyancy of a float. And that float in turn operates a little valve mechanism. In building service applications, we'd typically be looking at the FT or the float thermostatic trap that you can see on the top corner. The inverted bucket trap, that's more popular in process applications, such as oil refineries, chemical plants, and so forth. The thing that's attractive about the FT or float thermostatic trap is we've actually got two valve mechanisms in the one body. We've got the trap that works on the buoyancy principle, but we've also got that self-same thermostatic element that we have in the thermostatic trap. That means this type of trap is an excellent choice for venting air away. But again, we're typically only going to be locating this trap at the low point of the heat exchanger. We still need the air vent to be located at the occasional high point. If this trap's going to be located outside for any period of time, we're going to want to trace heat it or lag it, because it's likely we're always going to have some condensate that is held behind. And if that condensate is exposed to freezing conditions, it's going to crush the ball mechanism, which means the trap will fail in the open position whenever the steam system's energized again. So anyone that is familiar with steam systems will know if they come back after a Christmas shutdown, if they haven't drained the condensate away from the trap or ensured that this type of trap is lagged or insulated, then they can expect that they're going to have a number of failures on the hands. So the effect of undersizing a steam trap is evident. It means we're holding the condensate back, and we're going to encounter all of those issues with the wet steam that we've mentioned. But we always remember that we're likely to be exposed to issues if we've got an oversized trap. It means that if we've got an oversized trap, the mechanism is going to be working very close to its seat. It means the condensate is going to be pushed across the trap at a greater velocity than we expect, and therefore it means we're likely to get a lot of erosion, a high cost of maintenance of the trap, if you like, and ultimately a high failure. So it's vitally important that we size the trap correctly. So I'm just going to quickly run through a couple of trap sizing examples here. What we can see on the screen, it's an example of a typical process. We want to use the steam to elevate the temperature of a vat of hot water. We've calculated that we need 200 kilograms of steam per hour and that we need the steam at a pressure of 4 bar gauge, remembering that pressure temperature relationship. The pressure downstream of the trap, we've put that down as 0 bar gauge. So we've got 4 bar motive energy, or a differential pressure of 4 bar, that's capable of pushing the condensate away. We know that on this occasion, we're going to have a large mass of condensate to remove. So we know that a float trap is the perfect choice on this occasion. Well, every type of trap's got its own sizing curve. This shows you a typical curve for one of those float thermostatic traps. The line in green, that shows the condensate load. If we need 200 kilograms of steam to satisfy the requirements of the process, then the byproduct is that we need to remove the same mass of condensate. So we run the condensate load across horizontally. The line that's running vertically in red, that's that 4 bar gauge differential pressure. That's the motive energy that is present within the steam that is capable of pushing the condensate across the trap. So where the two intersect, that tells us how we size the steam trap. The problem is that only takes into account the running load. We need to remember that we need to double that running load to allow for that increased mass of condensate that exists when we're warming the heat exchanger up from cold. So instead, we look at where the orange line intersects with the red line, and that tells us the true and correct trap size. If we haven't taken into account that warming up load, basically means that trap's undersized, and ultimately we're going to have a number of issues, not only with the rate of heat exchange, but also the mechanical efficiency of the distribution network itself as that condensate backs up. The trap sizing methodology for removing the condensate from the infrastructure is slightly different, because we remember we've got a smaller mass that we need to remove, and the steam is going to exist at a higher pressure and a higher temperature. So on some occasions, many of our clients may have a second means of removing any condensate from the infrastructure. They may have that thermodynamic trap that we spoke about. They may also have a thermostatically operated trap. The benefit of having a thermostatically operated trap, it basically means that whenever we've got cold condensate in the infrastructure, where there's no steam present, there's no motive energy to drive that condensate away, it means that cold condensate can instead drain to waste, where it's not at risk of creating any mechanical damage in the infrastructure if it were to freeze or stand there for any period of time. The benefit of this type of trap is the cold condensate that's no financial value to us can be dumped to waste. Once the condensate increases in temperature to the point where it does have a value, this trap will close, and then that hot condensate will back up the leg and be diverted back to the boiler house across the thermodynamic trap. Simply put, if our client has the fixed temperature discharge trap as well as the thermodynamic trap, this trap is capable of diverting that higher warming up load away, leaving the second trap solely to take care of the running load. So, a sizing example for a thermodynamic trap. Again, if we're distributing 8,000 kilograms per hour of steam, 2% of which is 160 kilograms per hour, that's demonstrated by the green line. We run across to the red vertical line that demonstrates that differential pressure, 8-bar gauge. If we only need to take care of the running load, then it tells us that the low capacity trap is acceptable. But if the trap needs to take care of the running load and the warming up load, then you can see by observing the mass demonstrated on the orange line, it means that we need to ensure that we've got a high capacity of trap. Again, it just tells us how vitally important it is to ensure that we've taken into account the correct mass of condensate that needs to be removed. So in addition to the distribution pipe and the heat exchanger, the process, we also want to give thought to allowing the condensate to drain away from different parts of the infrastructure. We've spoken about the importance of those steam separators previously. A steam separator, it removes the moisture from the steam to protect certain components such as control valves, pressure reducing valves and flow meters from the effects of erosion. So we need to ensure that we've got a trap with a really good capacity, preferably a float trap, to drain that condensate away. And we also want to ensure that we've got an appropriate steam trap located ahead of isolation valves and control valves. Because if that control valve is modulating closed, or if we isolate the steam flow, any steam that is retained in the infrastructure is going to condense. So if we don't remove that condensate at the appropriate rate, whenever that control valve modulates open or wherever we open that isolation valve, we're more at risk of damage through excessive water hammer. So we appreciate the importance of sizing the trap itself correctly. We also want to size the pipe work correctly. So if we're condensing, let's say 100 kilograms per hour of steam, we know that the byproduct is going to be 100 kilograms per hour of condensate. We know that that condensate doesn't cool down. It exists at the same pressure and the same temperature, but we know it's got less energy contained within it. So when we're sizing the pipework that's conveying the condensate from the heat exchanger to the steam trap, that condensate's under pressure. It's a single phase, non-compressible fluid. But it's vitally important to remember that we need to take into account that warming up load. So we would always double, or better still triple, that 100 kilogram per hour, just to ensure that we're never at risk of the condensate backing up and flooding the heat exchanger. Because if that were to happen, then of course we'd get a very unreliable release of energy, very inconsistent release of energy into the process. and a longer warming up time, maybe a little damage to the heat exchanger in the form of water hammer. But as long as we take into account that increased warming up load, we can size that pipework on a water-based system, on a water chart. So simply put, we take 300 kilograms per hour, we run the line horizontally across, and it gives us guidance on the appropriate pipe diameter. Now, the problem that catches quite a lot of engineers out here is how we then size the pipework downstream of the steam trap. Remember, we need a pressure drop. So if that condensate is falling from 7-bar gauge, the steam tables tell us that at 7-bar gauge, there's 721 kilojoules of energy for every kilogram. If it falls in pressure, the energy content of that condensate must fall. And the only way that that condensate can give up its energy is by a certain mass or a certain percentage, boiling off, changing state to steam again. And of course, that steam is going to expand at a rate that is approximately to a factor of 1,673 times. So we need to size the pipework downstream of the steam trap to allow for that biphase. The chart over towards the right-hand side of the screen, it really demonstrates that if we looked at the top of the two bold red horizontal lines, it demonstrates that that pipework will be significantly undersized. Instead, we need to size on the diagonal dotted line to allow for that expanding biphase. If that pipework were undersized, the steam trap could be sized perfectly correctly, but if the pipework was undersized, that expansion would have nowhere to go. It'd expand, and unfortunately, that expansion would result in the condensate being held back and flooding the heat exchanger. The rate of heat exchange would extend significantly. Other points of good working practice, well, it means that each heat exchanger needs its own dedicated steam trap. We want to avoid the risk of bringing multiple condensate loads from different heat exchangers into one common trap. Basically, it means that we could have different mass loads of condensate existing at different pressures and temperatures, different volumes of flash steam that a trap needs to manage. And the risk is that any flash steam or condensate coming from one process, it could back up and it could affect the rate of heat exchange at another process. We want to ensure that each individual heat exchanger has got its own dedicated and correctly sized and selected trap. Now, that's not to say that the infrastructure downstream of the steam trap can't converge into one common infrastructure. Of course, it can. But it's vitally important that we give thought to the correct condensate loads, not just the mass flow, but also the volumetric flow that is dictated by the single phase liquid, but also by the resulting flash steam that's dictated by the pressure drop. The formula on the bottom of the screen, well, simply put, you can refer to calculators and configurators online that will allow you to determine how we size the infrastructure appropriately. So we appreciate that steam traps, they can and they will fail, especially if they haven't been sized, selected, installed, or maintained correctly. And when they fail, especially when they fail in the open position, that is going to manifest itself up those flash steam vents, as we've mentioned, because we need to protect the infrastructure from that expansion. The good news here is we can typically demonstrate the extent of that failure in financial terms if our client has benchmarked their cost of steam. So on this occasion, you can see that we've used the example of, let's say we've got a 1/2-inch steam trap operating at a pressure of 8-bar gauge, 6-bar gauge even, beg your pardon. Well, it tells us that if we know the operational number of hours, then we're able to determine what that inefficiency looks like in terms of energy loss. Now, obviously, that information is going to be of interest to an energy manager. What we can also do, especially if we've calculated our client's cost of steam, is we can calculate what that inefficiency looks like financially. Now, I've put an arbitrary £50 per tonne in place. That can vary considerably depending upon the gas tariff that our client may be on. I was working with a client just 2 weeks ago that told me their cost of steam was €212 per tonne. So you can appreciate that if they've got a significant number of failed traps, that cost is going to be significant. Now, typically, a rule of thumb that a lot of clients would work to is they would expect a failure rate of 1 in 10. So every 10 traps, one of them is likely to be in the failed position. Or if they install a steam trap, it would typically have a life expectancy of 10 years. That's a very, very broad rule of thumb. But if we look at a typical steam user, like an acute hospital, it's by no means unusual for them to have anywhere between 200 and 500 steam traps on site. With a 1 in 10 failure rate, you can appreciate what that inefficiency could look like. So that tells us that many of our clients are going to have a very, very robust steam trap monitoring regime. At the very, very least, they should have a yearly audit that physically inspects those steam traps to see, are they failed in the open position or are they failed in the closed position? If they are failed in the open or closed position, what's the reason behind it? Is it a correctly sized trap? Is it the correct type of trap? Is it installed correctly? Is it just poor maintenance or poor steam and condensate quality? An audit or report can quantify that inefficiency in financial terms so the client can understand the financial implication of not maintaining or replacing those traps, and it can make the appropriate recommendations for bringing the wider steam trap population up to optimal performance. Certain critical applications could have automated trap monitoring. But when a steam trap's failed in the closed position, the implications really depend upon where that trap's located. For example, if that trap's located behind a heat exchanger, the condensate can't get away. So that heat exchanger is going to fail very, very quickly. And if we're not getting hot water, for example, then we're going to be able to act upon that very, very quickly. The building manager is going to be aware of that very, very quickly. But if the steam trap's been removed for the failed for the purpose of removing condensate from the infrastructure, that's when the condensate is going to slowly back up and flood the steam line. And that's when we're going to get the erosion, corrosion, and water hammer creeping up on us over time. That's when the steam is going to slowly degrade and deteriorate, and our cost of steam is going to increase. So again, it explains the importance of having that appropriate steam trap audit on a regular basis. Well, so far we've spoken exclusively about the steam trap itself as an individual component, but it's important to remember that a steam trap should be considered as a station. We need to install a number of ancillaries to ensure that we can service and maintain that steam trap appropriately. So we may choose to have any number of isolation points upstream of the trap, a Y-type strainer, a check valve to prevent backflow of condensate when it's taken offline. The problem with a traditional station is we can have a number of connection points. So they are potential leak paths. It can be problematic for contractors to install because it can be quite time consuming. It can take up a huge footprint of space. And if we've got dissimilar metals, we're likely to get galvanitic corrosion. So many clients, hospitals especially, they've often got a preference for specifying a modular steam trapping station. Basically, it means we can pull all of those components into one common casting. It's cost effective to manufacture that casting out of an anti-corrosion material like 316 stainless. If we've minimized those leak paths, it means that not only are we not going to have galvanic corrosion, it means we're not going to have leaks. It's quicker, easier for the contractor to install. We've got a smaller footprint of space, but it also means that we can ensure that those steam traps can be repaired, maintained and serviced in line quickly and safely. But just to leave you on one last slide, whenever we're talking about steam traps, they are generic devices. There are a number of different manufacturers out there that offer different steam trap types. The one thing we want to do is when we're comparing different steam trap manufacturers, we want to make sure that we're talking the same language, that if we've taken a capacity of a trap from one manufacturer, we want to make sure it's comparable to another. So that's why we would typically use ISO 7842 as the comparable standard. If we know that the two traps are referring to the same standard, we've got peace of mind that they are going to be sized comparatively. So I'd like to thank you very much for your time. I've put a few points of summary up there on the screen. Essentially, the points that we want to remember is that we need to size a trap on the increased warming up load, not on the running load. We need to size the pipework in accordance with that flash steam that may be expected downstream. And we always size the trap on the mass flow rate of condensate and the differential pressure moving across the trap. So thank you for attending the fourth in the series of CPD presentations that we've put together that we're going to be running over the coming months. The next presentation on the topic of condensate management is due to be held at Wakefield. I believe it's at the Hepworth. So please do look out for that online. Please do look out for it on LinkedIn. And attendees will also be sent an email if they would like to register their attendance in advance. This particular presentation will also be uploaded onto CIBSE's YouTube channel in due course. So please do look out for it. Failing that, if there are any questions, either online or in the room, please don't hesitate to drop your message into the chat function or to give me a shout out. Or failing that, please do reach out to me at any point in the future, and I'd be more than happy to address any questions or comments that you may have. So once again, thank you very much for your attendance on this evening's presentation, and I look forward to presenting to you again in 4 weeks' time. Many thanks.